And we're live. Finally.
Yeah.
How's it going?
It's going pretty good. How are you doing, Abe?
I'm pretty good. We actually finally got to do this. So
I'm surprised.
I'm excited, to be honest. So, today is our first show. We're going to make sure this goes smoothly.
As smooth as you can do for a first time.
Yeah. And we can learn. I mean, there's an experience. At least for me. You're experienced, I heard.
You know, I've been told I have a face for radio, which is nice. You know,
You also have the voice for it.
Well, thank you.
Yes, you do.
So, Abe, what are we going to be talking about today?
Well, you know it. Let's start with the name of the show.
What's the name?
I know people can see it while they're watching, but right now this is From Atoms to Axons.
Atoms to Axons? What is that?
I love how you're acting all surprised, as if you don't you don't know what it is.
Oh, man, that name sounds so good. Who came up with it?
I wonder who. Bilal. So that's the name, and obviously there's two words in there, two keywords. Atoms.
From?
Well, yeah, but that's important, yeah.
Yeah, that's the key word, right?
Exactly. What is from?
Well, that's a philosophical question we can save for another day.
Let's just get to it, right?
Yeah. So let's start with atoms. What does the atoms represent?
Well, the atoms should be quite clear. Atoms means physics, because I am a physics major. And so, yeah, you're hearing that too?
Yeah, there's some weird...
There is some interference going on. It's cleared now.
Okay, cool.
So, the atoms clearly means physics, but I wonder what axons means. That's the question.
Well, axons, as you may or may not know, is the small part of the neuron inside the brain. So the cells that make up your brain cells are called neurons, and those cells are comprised of multiple parts, and the main part is an axon.
Oh, nice. So why choose axons? What are you studying?
Well, I'm studying neuroscience. What are you studying?
Ha! Neuroscience. I would love to do neuroscience, except I don't have the time. I'm already doing math and physics.
Math and physics, wow. Yeah. You must really be a nerd.
I get that a lot, but it's also true. Yeah, so today we thought we'd talk about electricity.
Electricity, but Abe.
Yeah.
You forgot the most important part of our show. We talk about atoms, yeah, physics, and axons, of course, neuroscience, but what else is there?
There's the best part of the show, actually, which I left out because it was going to come as a surprise. But we can just say right now.
I'd like to tell the audience.
Yeah, they should know. It's philosophy. And yes, for all you out there who just went, yay, yeah.
Yeah, all two of you out there.
All two of you.
All two of our 4 listeners.
And yes, we are live.
Yeah.
Treya, we are live.
I wonder who's listening. Oh, that guy's probably listening.
Is he, though?
Yeah, I'd say so.
So philosophy is going to be on the show, too.
Yeah, we'll bring up the kind of philosophical ideas that surround neuroscience, physics, things that can relate to whatever topic we're discussing that day. And as we get deeper and deeper into our shows and our discussions, I'm sure you'll have to turn down the volume because we're going to get pretty heated in here.
Oh, yeah. It's going to get so heated in here. But more importantly, we're going to start inviting guests. And that, I think, is going to be the highlight of the show, is having a few guests on the show so we can discuss some fairly debatable topics, but also fun topics, because they don't have to be all argumentative, you know.
That's true. Well, they could actually be guests that enjoy talking about physics and neuroscience, which
exactly.
It might be hard to find out there, but we'll find them. I'm sure we will, and we'll bring them on the show, and it'll be a good time.
There are plenty of them out there. If you're listening to us right now and you'd like to be part of the show, hit us up.
Yeah, you can reach out to either Abe or I anytime. You can email me at fo1832@wayne.edu.
And you can talk to me at fv1244.
FV, I always preferred FO.
Well, FV's the cool kids.
See, FO, it makes it sound pretty cool. It's like foe, man. This guy's about to be my enemy. So what was our topic for the day, Abe?
So we want to talk about electricity because that's the first thing that links neuroscience and physics, actually.
Oh,
and
how so?
Well, let's talk about neuroscience and neurons. That's your specialty. So I'd like to hear from you. How does electricity come into play?
Well, it's pretty interesting. Well,
Just
electricity.
generally, yeah.
What?
Just generally, tell me how.
Generally, well, basically, electricity has influence on the way that electricity and the brain work together. Are neurons communicate with each other through electricity and in between each other. So as the brain in its entirety is trying to communicate with the rest of the nervous system,
Mm-hmm.
it has to use electricity. It goes through an electrical process, and there's chemicals involved, and there's
Right.
neurotransmitters, and there's a whole mess of details that we can go into later. But
So the main fuel or the main driving force in our nervous system is electricity.
basically, yeah.
So I would assume that we have to start from there. Like, ask the question, what the heck is electricity, right?
Yeah, it's that good stuff that Benjamin Franklin gave to us.
We don't want to go there. I mean, you can always go back and back to the first person who discovered something.
Yeah,
and talk
Benjamin
about
Franklin. Who else? There's no one else.
it. There are a lot of people.
No, just Ben Franklin. I can't imagine anyone else with significance.
What about Thomas Edison, Nikola Tesla,
no.
James Clerk Maxwell?
No, I think
Michael Faraday.
I just say Benjamin Franklin. He's on the 100, so he's more important.
Oh, that's true. If you're hearing us, we need some couple of hundreds.
Yeah, send them our way so we can really debate this topic properly.
Oh, yeah. So, if we want to just start from the basics and talk about what electricity really is, there is a fact in the universe that electric charges exist. So, what the heck is electricity? Well, there are certain properties in the world that exist. So, for example, you right now are wearing a maroon shirt.
I'd say maroon, yeah.
Yeah. So the maroon is a property of your shirt, right? And then you also have a certain mass. You also have a certain height. So
I don't like to talk about it.
Nobody likes to, but that's why I'm talking in general terms. And so these properties are what sort of define you as a Bilal, right?
Yeah,
And
you
so
could say
there's
that.
this property in the universe that's called charge, right? And it comes in
Charge, like with your phone?
exactly. That's actually, yes. You can charge your phone through these processes, and
Oh.
we'll get to that.
Kind of like how if you put your phone in the microwave, it just charges it right away.
It's gonna maybe not the same way, but you can put your phone in a microwave, and then you're not going to like the results.
Yeah, for all of you out there who think that works, don't
Yeah, don't do that.
don't actually.
We don't have to say this, but we have to. Going back to charge, yeah. So it is a basic fact of the universe, and it comes in sort of three modes, if you want. There is the so-called negative charge, and there's the so-called positive charge, and there's this thing in between called neutral. So,
Like Switzerland.
like Switzerland, exactly. It's always in between, never taking decisions. But so the negative charges, or should I say the like charges, repel each other, and the opposite charges attract one another. So if you want to flirt with a certain someone, then electricity is one way to go.
So would that be a positive or a negative charge?
Well, as long as you're opposite charged, then you're going to attract.
And if we're negatively charged,
Then you're going to, if you're both negatively charged, well, I got bad news for you.
we're going to repel, aren't we?
You're going to repel really badly.
That explains a lot.
It does explain. And one thing I wanted to mention is that a lot of people don't appreciate just how much electricity and electric force is present throughout their lives. Because really, the electric force is what holds our universe together. And this is not an overstatement. This is really what's going on. I mean, just think about it for a second. This table that we're sitting on right now.
We're
this
sitting on the
chair.
table.
Yeah. No. That's in front of us. The
These
chairs we're
chairs.
sitting on, the
Uh-huh.
laptop I'm using, the microphone, they're all made up of atoms and molecules and all that stuff.
Adams, look, we said the name
We
in the
said
show.
Every time we say the name, or at least a word,
We take fish.
we have to, I don't know,
I don't
do
know.
something. We put a 50 cent in the jar or something.
Every time we say a word, we put 50 cents in the jar.
The word that's in our name.
Oh, I see.
Yeah.
So
every
what about
time-
the word from? Would that?
That doesn't count.
Are you sure?
Otherwise, I'd be broke by the end of the show.
I'm already broke, and I said it once.
So, how does it hold everything together? Well, these atoms and molecules, actually, you wouldn't have atoms without the electric force. You wouldn't have molecules without the electric force, because the attractive force between these molecules is what keeps everything together.
Molecules?
And without it, yeah, even molecules, because it turns out that molecules actually have some sort of attractive force between them before they start repelling each other. It's only when you get too close that they start repelling each other.
And it's electricity that guides this.
It's the electric force, exactly.
Interesting.
And what's amazing about the electric force is that it's enormously strong compared to gravity.
Is it like the force? Is it different than gravity then?
They actually have pretty similar mechanisms, almost the same mechanisms. If you write down the law of gravity and the law of the electric force, you'll see they're exactly the same, except for one deals with masses and the other deals with charges. But other than that, they behave exactly the same way.
Huh.
Oh, the difference between them is they have different strengths, and this is what actually one of the big problems right now in physics. They're trying to figure out why these different forces have their strengths. So let me give you an example. Right now, the whole Earth is trying to pull me down to the center of the Earth.
Oh man, do I feel that? Earth's always got you down.
It got me down, yeah. And it's also pulling my phone down. However, I can simply just lift up my phone. I just did it. You can't see me, but I just did it.
Tough guy over here.
Yeah. And so how did I do that? I mean, the whole Earth is pulling on my phone, and I can lift it with ease. So the answer is pretty much that the electric force is so much stronger than gravity that we could lift things up, we could defeat gravity every time.
Interesting. So is there ever a case where the gravitational force is greater than the electrical force? Like,
of course,
what
you
about a
could
black hole?
cook up systems exactly like a black hole, which has enormous gravity past like the event horizon, for example.
Right.
And so you could have certain situations where the gravitational force would be stronger than the electric force, but those are sort of very special cases that you almost never see.
Right. So anything that would practically apply to us would be
exactly, the electric force would be much stronger. It also is responsible for many, many things, like take light, for example, like light.
I do like light.
Yeah, light. What the heck is light? Well, it's actually an electromagnetic wave. It comes from the electric and magnetic fields.
So you're telling me the electromagnetic waves are made up of the photons, or vice versa?
Right. So if we want to start talking about photons, then it gets a little murky because then you have to involve quantum mechanics.
Oh, let's stay away from that.
Yeah, let's stay away from that. For all you experts out there watching, and you're looking for those tiny details to pick on us, don't do that, please.
Yeah, we'll stay away from those topics.
We're staying classical here. So it turns out that light, even radio waves, even X-rays, even UV light, is all just one thing. It's an electromagnetic wave, but with different wavelengths, and that's how you have these different types of light.
So even gamma rays?
Even gamma rays.
So does nuclear radiation have to deal with electromagnetic waves?
Yeah, exactly. So
So it really does get involved in everything we do.
It does. And so take rainbows, for example.
What about a double rainbow?
In fact, there are always double rainbows.
Wait, really?
It's just, yeah, the second rainbow is usually too faint to see, but it's always there. And you can prove this using the laws of electricity and magnetism.
What about a triple rainbow? Or are we asking for too much here?
Now you're asking for too much.
Okay.
I hope God created triple rainbows, and we just haven't found it. But the cool thing about the double rainbow is, maybe people haven't noticed this, but the colors are always reversed.
It's not Roy G. Biv?
It's the other way around. So if you look at the normal rainbow and you start from red and go to the violet, and then you look at the other rainbow, you'll notice that the light is actually flipped. And that has to do with refraction and all that fun stuff, but that's for another time. Take sunsets, the beautiful sunsets.
I do love sunsets.
You do love sunsets. Why do we have sunsets? Well, it's also because of these electromagnetic waves scattering in the atmosphere, and then you end up with these beautiful lights. The blue light actually scatters way too much. That's why when you look at the sun, you won't see any blue because all the blue is going away from you.
Huh.
And then the red light does not scatter that much, and that's why when you look at the sunset, the red light is not scattering, so it's coming to your eye. And that's
so
why
electromagnetism really has to do with scattering light, with different rays, with different waves, and it truly encompasses everything that's involved in our physical world.
Pretty much. Even life itself.
Wow.
Yes.
So back on topic, off our little tangents of light, how does electricity have a more practical use?
So right now we're using it, and I don't have to explain that because it's quite obvious. But let's talk about this basic principle of how we really have electricity, and what are some misconceptions that are floating out there. because I've heard quite a few, and I'd like to get those straightened out. So, electricity is a lot like water, right? Water flows, and especially it flows from higher elevations to lower ones, right?
Right.
So if you have a pipe that's 10 meters above the ground, and you have one, yes, I'm using.
Can we?
Yes, I'm using the metric system.
You have to use
because
why?
Because
This is America.
this is America, but the metric system is just superior.
It is not superior. Let's save the debates for later, because I
You want to hear about electricity?
want to hear about electricity, and I don't want to start this discussion here.
I have a great video for you about the imperial system and
I-
how it's just chaotic.
I have this great thing for you. It's called freedom and liberty and the pursuit of happiness. You should look into it sometime.
Oh, all right, I'll do that. So, as I was saying, like water flows from higher elevations to lower ones. The same thing happens with electricity. It actually goes from higher voltage, to use that word, to lower voltage. And you can just think about voltage as this separation between higher elevation to lower elevation.
So naturally, electricity wants to flow from a higher voltage to a lower voltage.
Exactly. Exactly.
That's funny. There's a cool concept in neuroscience that uses that practically in every
I
thought
want
we
to hear
have.
that.
We'll
We're
get
gonna
into that in
to
a second, but let's continue with what you're talking about.
So, whenever you have electricity, the two main components that people usually hear are these voltage and current terms. And basically what voltage is, as I explained, is sort of the difference in the energy. If I have a ball at the top of a building and a ball at the bottom of the building, we know intuitively that the ball at the top of the building has a lot more energy because
Because of the
merely
potential.
exactly, the potential energy. Merely just dropping it, it would gain a lot of speed.
So what you're saying is, when we compare ourselves, you would have a lot of energy and I wouldn't, because you have plenty of potential and, well,
In life,
yes.
I mean, that is a fact, but we don't have to-
Whoa, okay. That wasn't a very nice save.
You brought it to yourself. So
naturally flows. And what kind of speed do we expect here?
that's actually a great question, because usually what people think when they're talking about electricity is that, I flick a switch and then the light turns on almost instantaneously, right? So we sort of draw this conclusion that the electrons in the wire, or the charges, they don't necessarily have to be electrons, but the charges in the wire are moving so fast that we get this instantaneous light turning on, right?
It's not.
In fact, and this is going to shock some people out there,
Ha.
pun intended, electrons actually move slower than turtles.
Wait, what?
And this is hard to understand unless I tell you about this analogy. Say you have a domino next to another domino, next to another domino.
Like a pizza?
Well, I like Little Caesars, but I don't want to sponsor anyone here.
It's legit.
That's pretty good. Yeah. So you have these dominoes stacked up, and then you hit one domino, and you know how the rest of them cascade down, right?
Yeah, the domino effect.
Exactly. So what happens with electricity is that the first electron, there is no, first, but just go with me on this one. It bumps with the second one, and then which bumps the third one, and then bumps the fourth one, and so on and so forth, until you reach your whatever you hooked up to the electric power lines.
And that's what's much faster and what triggers the light to turn on at that instantaneous rate that we perceive.
That's exactly it. It's the collective behavior that is almost at the speed of light. And
Really?
yeah, it's so fast. But the electrons themselves are actually moving really slowly. And you can calculate this. They do this in like basic physics classes, but it's astonishing.
So how fast are we talking?
For electrons or for the electricity?
For electrons.
For electrons. So you're talking about 0.0000001% the speed of light. I may have missed a zero there, but that's slower than turtles, literally.
Huh.
That's
So
awesome.
what about the other one?
Electricity is super fast, to use the technical term. it's
So
like,
fast.
It's almost the speed of light. It's
Oh,
almost
wow.
the speed
Okay.
of light.
So
yes.
comparably, they share a lot of properties and they're comparable in speeds as well.
Right, they're very comparable, yeah.
Am I comparable to that speed? Like, do you think I could outrun electricity?
I guess if you like train with Usain Bolt, perhaps, and then
Get
I
hit
don't
by a
know.
meteor and some
Get-
lightning at the same time.
perhaps, and then Einstein would come to you because you'd start violating relativity and stuff.
He'd
But-
tell me I'm doing the wrong thing. He'd yell at me.
you're ruining my equations.
Oh,
He would say in a German accent.
all right. So
So
very
that was-
fast electricity, slow electrons. Kind of getting this idea.
Yeah.
So why is it that electricity flows so slowly?
So the reason is there is this analogy that we could try to understand it from. If you have a person walking in a room and there's just a lot of people in that room, and this person is really famous, and they're trying to get to the other door, right? So they walk into the room, and then this guy sees them, and they start shaking hands and talking, and then they have to go back a little to say hi to this person, and then you go forward a little bit, and then you meet this other person. So you sort of get lagged in the room, right?
Oh, because they have to make contact with everything.
Exactly. But if you look at the bigger picture, you're actually making progress. You are moving towards the door. You're just being lagged by these people, right?
This sounds like an Arab goodbye. If you're familiar with those.
You can explain that.
So, in the Arab culture, I'd say the process of saying goodbye, when your parents tell you, hey, we're about to leave, that means you have literally at least an hour to do what you were doing, because the goodbye process is a process of every single person interacting with another person for at least 5 minutes. And there is progress. It's very, very slow, but the progress is there. And by the time you reach your goodbyes, it has, time has passed significantly.
And
I'd say
that's-
0.00000.1% the speed of light. Yeah, I
Dang,
threw in an extra zero there. Slower than turtles, man.
slower. Wow.
Mm-hmm.
But that's basically the analogy, and that's how the electrons sort of move from one place to another, even though they're being sort of going all over the place.
Mm-hmm.
And so this is sort of the basics of electricity, and
At least in regards to physics.
in regards to physics, of course. Now, we're still waiting to hear on the other cool part of the show, which talks about, what does it talk about?
Well, I remember the name. I think it was Axon.
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 What's an axon?
Well,
That's what I want to know.
so here's the fun part. Electricity, not only in the physical sense, but in the anatomy sense, it has to basically, it contributes to everything that we do in regards to our nervous system. How?
How?
How do you ask?
I want to know how.
Well, let me tell you. It's really fun, and I find it fascinating. Personally, I don't know how others feel, but it's really cool. So, starting in the big picture, the brain is comprised of many, many neurons. Now, these neurons are the brain cells, and they're composed of multiple parts, including the cell body, the dendrites, the axon.
Now you're
and-
gonna have to tell me what a dendrite is.
All
'cause
right.
That sounds pretty weird.
It's not like dandruff. It's a little bit different. It's not flaky. So if we have to explain what an axon or what a neuron looks like, we'd start with the head
Mhm.
or the tail. We'll call it the tail. That's composed of these dendrites, and these dendrites are like branch out, areas that kind of branch out and try to receive data from other neurons.
Okay, gotcha.
Then we have the actual axon itself, which is a long, just a long piece
Mm-hmm.
that has myelinated sheaths. Now, these myelinated sheaths are crucial into what conducts electricity within a neuron. And we'll get back to that in a sec, but let me finish
Okay.
this. And then you have the axon that continues on with, again, somewhat like a branch-like head that communicates to the other.
Also, like one part of it tries to
receive it.
intercept, receive.
Right, and the other sends it out.
Gotcha.
So, how does a neuron communicate within itself? Because we have to start with the smaller picture before we can look at the big brain itself.
Right.
So,
So-called emergence.
right. So the brain, or the neurons communicate through electricity from one side to the other. This is done by a process that is called an action potential.
Okay.
Now, this action potential takes a huge amount of effort
Mhm.
to build. And once a certain threshold is reached, it fires. And this firing process is what shoots the electricity from one myelinated sheath to the other.
So you can only have an action potential as soon as you cross this threshold limit.
Exactly. And
And that's a
following,
threshold in what exactly? Is it a threshold?
it's in P. It's in a. What was the name for it?
Is it like voltage?
Exactly, in the voltage,
Okay.
which is about negative 35 volts, I want to say.
Millivolts, yeah.
Millivolts, yeah. Not volts, that would be unfortunate. So negative 35 millivolts is about the threshold that you want to reach. Once it reaches that, there is a kind of dip inside the action potential where the another firing of an action potential cannot occur for that period. It's called a depolarized process. It's the depolarized phase. So the way that it continues to work is it shoots from one myelinated sheath, which is kind of like a little piece of fat that wraps around the axon and helps it communicate from one to the next.
So it's kind of like clothes. It's wearing something.
Sure. Let's just say they help the neuron communicate between itself much more efficiently. Without the
But why?
Well,
how does wearing clothes do that?
Well, think about it this way. There are either a long stretch that your electricity has to pass through,
Okay.
and that takes time,
Right.
or you can have short little intervals that are referred to as the nodes of Revier. Pardon
This
me.
guy,
Ranvier,
his
who's the
name.
man who discovered it, makes sense.
Ranvier.
Yeah, the French, if you want to get into the metrics and all that. I prefer the American way. But it's these nodes where the electricity jumps from each myelinated sheath to the next, and it speeds along the process and builds exponentially. That's why in a lot of neurological disorders, there's degeneration inside the myelinated sheaths, and because these myelinated sheaths are degenerating, it's flowing. The electricity is flowing much slower, and the mental process, the cognitive process, slows down incredibly, and that's how you have a lot of these neurodegenerative disorders that occur, kind of like Parkinson's.
Oh.
And we can go more into that later.
So when you have this myelin sheath, then you sort of have a jump from one part to the other, and that's how you have this accelerated movement. So the electricity sort of.
Exactly.
Oh.
So this jumping process, and how is that jumping process done? It takes us back to that topic we discussed of flow, the flow of electricity, how it wants to flow from a negative to a positive.
Mm-hmm.
Inside the brain, there's this inside the neuron itself, there's this thing called the sodium-potassium pump, and this pump constantly is pumping in and out. Yeah, right. Sodium and potassium, which are both positively charged, depending on the charge of the inside and outside of the cell body. So if the inside of the cell is negatively charged and the outside is positively charged, well, which way does the electricity want to flow?
Well, it flows, so the negative charges want to get away from the negative charge region, and the positive charges want to go to the negative region, so inside. So the positive charges outside want to go inside?
Exactly. So the positive potassium and sodium will flow into the cell, and that helps the electricity transfer from one to the next, and that is part of the action potential. Do you see where this is going, Abe?
To the current.
Exactly. So, and vice versa, obviously, if there is a negatively charged outside, positively charged inside, the sodium and potassium will want to rush out of the cell. So these are details that we don't need to get into.
But that's basically how this electric message is sent through neurons.
And how the principles of electricity apply to the neurons and how it applies to cognition in general. Because now we get to the larger scale. How does a neuron communicate from one to the next? The neuron communicates through a process of chemicals that are sent from one to the other, and these chemicals are referred to as neurotransmitters.
So you showed me a picture where there was all these dendrites going out, and the axon had a lot of those tentacles coming out.
Yes.
And so you're saying that two neurons are really close to each other, and then one of them has these dendrites on one side, and the other one has the axon tails on the other.
And they kind of like, if you ever seen any sort of docking of a spaceship,
Yep.
Yeah, you know exactly what I'm talking about. Where International Space Station kind of has a craft that's locked in. It kind of locks in.
Okay.
And in that process, it sends a neurotransmitter to the other one, and it opens up different gates. And again, a lot of details here, but it
just
sends
a general picture.
Right. Yeah. It sends neurotransmitters from one to the other, and these chemical neurotransmitters, these chemical signals, and you might be familiar with some of these. There's dopamine, there's serotonin.
Oh, yeah, we hear about all those.
Right, and these are pretty common ones that people know about. And these are the ones that are transmitted from the brain. And the big issue, the reason why they're always talked about, is because the brain has this thing called the blood-brain barrier. It's very interesting, but it basically prevents anything that's ingested, something that's coming from the stomach, from the body itself, from going to the brain. This is done because you don't want, if you're sick, if your body is sick, if it gets to your brain has no way of fighting that off, and it would do some severe damage, and that's why...
So it just blocks it.
Exactly, it blocks it there, and that's why if you take any sort of medicine, orally, you can't really get beyond the blood-brain barrier. So you have to take something called an SSRI, which is a selective serotonin reuptake inhibitor, which is kind of an alternative way of getting past this.
So you're sort of cheating the system.
Kind of cheating the system. It's really interesting. It's like getting over the border without a passport. It's a way to do it. There's possibilities. It's possible. It's just not very common.
So that's why sort of people go for other means of taking in substances if they want faster or better.
That has to do with how quickly you can access the bloodstream. So like if you're... Let's not talk about drugs here. But yeah, there are different ways to take medicine, and that affects how quickly it affects you.
Yeah, like anesthesia. I mean,
exactly.
You just put it into the bloodstream directly, right?
Mm-hmm. So, again, this all has to do with how electricity flows from one neuron to the next, and how, big picture, they communicate in the brain, and how each one leads to a thought, and how thoughts are made, and how if I am firing constantly, and I'm doing the same routine where this one neuron is firing to this other neuron, how it builds the strength between them, because if it's reoccurring, just kind of like with muscle memory, it builds that constant strength. And
so the more the same neurons fire, then the more intertwined they will be?
There's an excellent way to put that, Abe, that a famous, well, it's actually, you could say this man plagiarized, but he basically coined this term, and it made him famous over the man who actually discovered it. But
we have a lot of those in science, don't we?
Plagiarize. So it's called, the quote is, neurons that fire together, wire together. And simply put, the neurons that are constantly, working together, that are always firing because you're always having this thought or practicing this one skill, are eventually going to get stronger and better. And that's why you become better and better at skills the more you practice them, because your neurons are wiring together and becoming stronger.
So if I want to master Mozart's Turkish March, then I better sit on the piano for 9 hours and just go ahead and practice.
Yeah, or you could have a life. It depends.
I mean, my life is the piano, so...
Is it physics? Is it math? Is it piano? You got to choose
one.
A
lot of things.
Is it chess?
Oh, chess is half my life.
Yeah.
But so, okay, that makes a lot of sense to me, because I know when I do something when I repeat something too many times, then I know I could do it almost subconsciously. So
yeah, and that's part of that process. Off on a tangent of electricity and how it affects the brain, it's very, very cool, and I find it fascinating because I love the brain. I love the ways that it operates, and electricity plays a huge part of that, and that's why physics is such a interesting topic to bring in, because they work so well together.
Right, it's very tied to the mechanisms of modern day biology, pretty much.
Right, it's like we're patting ourselves on the back for coming up with this show. Good job.
I know the brain is the most complex.
I think you're the most complex, Abe.
That is actually, there is some merit to that, in like personality-wise, maybe. But the brain as sort of a machine or as sort of a faculty is perhaps the most complex thing we've ever found.
So can you tell me more about electricity, Abe? I'd like to hear so much more.
I can talk about electricity all day long, and what I want to focus on for a second is how electricity can generate light. So we know that electricity is generated by these charges, and what Michael Faraday actually noticed is that if you think about a charge and the surroundings of the charge, then you can actually model it as if there's some sort of field surrounding this charge. So the same way in Star Wars you hear about the force field, then it's actually a lot similar to...
Let's not bring in Star Wars into a topic of science.
But
I feel like we're going to get things a little murkied.
Analogies are good.
Okay. As long as it's an analogy.
To a point, yeah. And I'm also a Star Wars fan. So for all you listeners out there, hello there.
Stop. Stop, Mr. Cannoli.
But
Well-
yeah, so Michael Faraday had this idea that there is this electric field that sort of permeates all of space. And what the heck is a field? It's just take any point in space, there is a number assigned to this location, either, say, +5 or -63 or 0, perhaps. And so that's exactly what a field is. It's just some sort of value at every point in space. And then he also looked at magnetism, and he noticed very similar things until James Maxwell came along, and then he noticed that you can actually merge these two fields together, the electric field and the magnetic field, to
Is that
one single field called the electromagnetic field.
Would you say that's how the planet works?
Say that again?
Would you say that's how the planet operates with the use of this electromagnetic field?
It's every phenomenon you see on the planet is basically governed by this electromagnetic field.
Wow.
And
It's a lot of
so
pressure.
it's, yeah, get it right. So every time you look at a magnet, or you look at light, or you're repelling someone, then it's all manifestations of one single entity called the electromagnetic field.
Speaking of repelling someone, that's gotta suck. You know, puts you down in a bad mood. Speaking of being in a bad mood, look at me going on tangents.
How do people get into bad moods?
Over time, I'd say, you know, a lot of stress, a lot of things on their plate, eventually builds up, and you just can't handle anymore. People who take on too much or are exposed to new things can burn out, can quickly realize that they need help and they're struggling.
Are there certain neurotransmitters linked to changes in mood?
There have been studies that show serotonin is linked to mood changes, which is why a lot of antidepressants contain they're like a serotonin supplement, I guess, in the simplest way to put it.
So there's a lot of interplay between biology and sort of psychology, or mental states and physical states.
Yeah, I'd say so. And if you ever are feeling down and are put in one of these bad moods, or just need someone to talk to and are having a rough time, especially here, we're at the university, I'd say reach out to CAPS. CAPS is this really cool program that the university offers. It's career center.
Counseling.
It's a center for. Actually, hold on. Let me pull up the exact acronym.
I had a friend who went to CAPS, and they tremendously benefited from it. So I would also highly suggest CAPS if you're ever feeling down, if you're stressed from.
It definitely helps out. I know that in the past 2 years, it's grown. The program has grown exponentially, and I've known a handful of people who've gone in and benefited a lot because they really do help you out. It's kind of like a place to talk to someone, a place to kind of help improve your mental health, anything that might be keeping you down.
Where is it located? Do you know?
CAPS is located on the 6th floor of the student center, so you can head on up there, take the elevator, and you'll see signs that point you in the direction, and once you walk in, they'll take you through the steps and just help you out.
Oh, that's pretty cool.
So just to let you know, CAPS stands for Counseling and Psychological Services. It's basically services that are offered to all students here at Wayne State. And that's going to be our PSA for the evening. Excuse me and Abe as we take a quick intermission. We'll be back in 5 minutes, and get ready, get set, prepare your notes as we're going to be diving into our philosophical topics after this. And we're back. Hello.
That was a nice intermission.
It was. We got some yogurt and some water.
We've been talking for, I think it was 40 minutes. I did not feel them.
Yeah, it
They
felt
went
like an electron.
No, you got it.
Oh, no, wait.
opposite.
It felt like electricity. Really fast.
We'd like to give a few shout-outs as we come to the end of the show.
Well, this is in part because of the wild support we've gotten from the Tetraquark. Shout out to Chloe, Diana,
And Shreya.
Mehdi.
Sal, are you watching?
All our boys and girls back home. So, thanks again for listening. We can't wait to have you guys on next week. Speaking of next week, our showtime is going to start at 6 o'clock. That'll be our normally scheduled showtime, 6 to 7.
Make sure you tune in.
Oh, yeah.
We're gonna have a guest.
Probably a guest star, and we'll have some more philosophy sprinkled in with the sciences.
Yep, and then we're gonna have a lot more detailed discussions, probably.
I'm looking forward to it.
Me too.
So to wrap up this electricity topic for the day, how would you like to go about that, Abe?
So, I guess when we're talking about electricity, then really just remember just how amazing that these phenomena we experience daily are, and how everything is sort of linked together in a way, not in a
Spiritual
voodoo,
way.
pseudo way, and
In an
type-
actual real
in an
science
actual-
way.
yeah, like quantifiable way,
Okay.
and how it's linked to neurotransmitters, to neurons,
To the brain.
to the brain, and
How all our thoughts
our
and
motor function. Yeah.
I guess speaking of going back to the yogurt, how does our diet really affect our brain, the way our myelinated sheaths exist, and how strong they are, and what the difference is between having poor diet and having a weak or deteriorated myelinated sheath and having a good diet. Because remember, ultimately, these sheaths are made out of little
said
pieces,
fat,
little
right?
pieces of fat, that surround the axon, and that's crucial to understand how much influence they have on our brain, and how much how importance they carry. Because
So what
plenty-
are,
go ahead.
what are what are some of the effects of having a neuron that's sort of not functioning properly without its myelin sheath, or perhaps just it's without its myelin sheath? Does that have any effects? Would that slow down certain motor functions?
Well, yeah. So in the case of multiple sclerosis, in the case of MS, one of the big issues one of the symptoms that occur because of it is the deterioration of the myelinated sheaths, and what accompanies it is lower motor function and poor, very slow thought process, very slow output. So it's a very destructive disease, and that's why it's renowned so heavily in our society, because it destroys these myelinated sheaths. Another one is Parkinson's, when you quickly lose control of over your motor function, so you can no longer really start and finish your actions. You have to. It's kind of just.
It'd be hard to dance, sort of.
It's
hard to move,
yeah.
hard to. Yeah. Speaking of dancing.
So speaking of dancing, go from a sad topic to a lighter one.
Lighter one.
If you guys are free on Mondays and Thursday nights, go check out Swing Club over in Dance Room 20 in the Student Center. They're always dancing and swinging, having a good time. It's free, it's fun, and anyone can do it. I'd recommend it to anybody, even if you have 2 left feet, 1 left foot, no feet. Yeah, even if you have no feet, it's a good time. You show up, we spin you on the floor, everyone laughs.
You'll have a great time.
It's a grand old time.
And
Abe, can you speak to that?
I mean, I have been spun before by you, Bidad, and it was a great experience.
Would you say it's easy?
It's easy to pick up. Yes, I would definitely say that. It's also fun, and I would definitely recommend it for those people.
Yeah, so once again, it's on Mondays and Thursdays from 7 to 9 in Dance Room 20 in the Student Center.
So that's the basement.
Yeah,
right?
the basement. We look forward to seeing you guys. So, electricity. There's plenty of that there.
There's lots of people moving around.
Yeah, it's a good time. So, Abe, tell me, why physics? What attracted you to physics?
Pun intended.
Yeah.
Basically, with physics, I actually had. If I want to tell you the story of how I got interested in physics, it's quite funny, because I sort of was never interested in physics deeply until
What?
yeah,
Hey,
shocker.
But it's physics.
It was like until sort of 11th grade, 12th grade is when I discovered this YouTube channel called Veritasium, and I kid you not, it had some of the greatest videos.
You're telling me a YouTube channel
has
gotten you into physics.
Right. So usually you hear these great professors talk about how they were inspired by some sort of book by Stephen Hawking or by some other pop sci writer.
No, you just
like
was
Brian
inspired. You were inspired by a chiseled gin British man.
Greene. Exactly. He was.
Wow.
I think he's Australian.
Oh, okay.
Yeah. But the thing is with YouTube, and especially when I first was introduced to it by my brother, actually, I was learning about all this physics, but also through video, and so it's not sort of a boring way of learning something. It's a passive way, and you're actually watching someone, and you're watching an experiment being performed in front of your eyes. And so it started from there, actually. The first video I watched was on quantum computing and how an electron could be in a quantum superposition of a spin up and a spin down. And I just wanted to know more after that.
Fascinating. Sounds absolutely fascinating.
It's super fascinating.
Can't wait to hear more about it.
I'll
Not now.
This is a topic in itself.
Yeah.
But so that was basically how I started
Well, it must be
appreciating
nice.
the physics. And then I just started learning more and more. I talked to my teachers, and I expressed interest in physics. And then I decided to major in it and hopefully become a professor of physics.
You know, it's nice to have dreams.
It is nice.
Dreams are nice.
Dreams, a lot of them, but they can be accomplished.
Yeah. I believe in you, Abe.
Thank you.
It's
I believe in
interesting.
you too.
Thanks. Much appreciated. It's actually very interesting how a lot of people who get into the fields that they enjoy and things that they're passionate about is through YouTube and watching things on video. It's nice that we can hopefully have that same effect over just voice over the radio.
I really hope so too. How did you get into neuroscience in like 1 minute?
1 minute neuroscience? Man, this sounds like a cool idea for a YouTube video. Oh, well, it started all in high school. I took my first psychology class and absolutely loved it. I quickly realized how much the brain was just an absolutely fascinating organ. There were so many things we didn't know about it, and I wanted to learn more. I wanted to know everything there was to know.
Curiosity.
Right.
Yeah.
So curiosity took the better of me, and I enjoyed psychology, but I absolutely adored neuroscience and the sciences and the chemicals and everything behind the way the brain exists.
Actually functions.
Right.
Yeah.
The cognition and the behavioral aspect of how all of our neurons and everything in our nervous system kind of works together. And yeah, that took me into this.
It's kind of sad that nowadays it's really hard to become a polymath. Like back in the day, someone knew physics and chemistry and math, and he was everything. He knew it all.
Well,
but
nowadays,
nowadays you barely can finish like one field before your mind explodes.
Oh, well, that's why you're such a phenomenon, Abe. Physics and math. Wow. So intense.
Thank you, Bilad. I think that's all the time we have for today, and we'd like to thank our listeners.
Yeah, thanks to everybody out there who was listening today. We truly appreciate you guys. We can't wait to have you back on next week.
Next week at
6 p.m.
Thank you very much.
This has been From Atoms to Axons with
Bilad and Abe.
Yeah. Have a good day.